Thank you for the introduction. We are all familiar with a figure that looks a little bit like this, dictating and describing the decline in biodiversity, the loss of biodiversity. These indicators are incredibly influential. For instance, every year or two, when one of those indicators comes out, they make headline news, but they're also influential within the policy sphere and often shape not only the public's and policymakers' opinion about biodiversity change, but also dictate our own too. However, these indices of biodiversity change are also subject to an awful lot of scrutiny and are debated intensely. For instance, in 2020, Brian Lung came out with the paper Clustered versus Catastrophic Declines, and 4 different people responded to the article with their own concerns or queries, often around technical details such as how these metrics, how these indicators are derived, all the way through to the intricacies of what they actually mean. And from my own prior experience, there's a lot of this debate actually is centered around, we have this impression that biodiversity is declining, but how can we accurately and representatively describe that decline? And so maybe it would be helpful if I just sort of describe what these indices are made of. So the underlying data for these indices, and by these indices, maybe I should just say these are like things like the Living Planet Index, the Breeding Bird Index. There's moth-based indices. There's a whole array of these, and they're really influential. And part of the reason they're so influential is that they are derived by some of the richest biodiversity data available. There are now cumulatively across all of these different biodiversity data sets, we're talking about 50 million abundance values for 40,000 species, covering 150,000 unique locations and stretching in time back from the early 1900s through to today. So really rich data, and that adds an awful lot of weight to the value of these indices. And when confronted with this data, there is an awful lot of complexity that we've got to wrangle. Even just looking on this map here, where each of these different dots represents a different population, there are some really clear complex structures within this data. For instance, it's evident there is bias within the spatial bias, but there's also likely some taxonomic bias. We know we measure certain species more than others. There's temporal bias. There's likely some bias in the environmental structure. For instance, maybe we know that we are measuring populations in areas that are more protected than areas which are less protected. We don't tend to monitor biodiversity on the frontier of destruction in the Amazon. We tend to monitor biodiversity where Maria is now, in the Kalahari. I think there is actually a dot for the Kalahari there. And so when confronted with this complexity, we really want to try and isolate out the signal from the noise. We want to be able to wrangle it effectively. And there are 2 common approaches within the scientific literature to do that, which I term the random intercept model and the random slope model. And these 2 approaches are, and we did a literature search as part of the postdoc I'm just finishing off now. And across hundreds of articles, it was apparent that these 2 approaches are used about 50-50. And a few little niche approaches are also available, but are barely applied. So the random intercept model, at its core, is trying to describe the change in abundance with time. And it recognizes that there is some hierarchical structure in here, because us ecologists love mixed models. And so they specify within this model that there is a different mean abundance in different populations, locations, and species. And that's the mean abundance difference. And that's accounted for with a random intercept term. Now, the slightly more complicated version, which would currently be considered cutting edge in the literature, is a random slope model. And here again, the objective is to derive this abundance year coefficient, the change in abundance over time. But this time, instead of just specifying the difference in mean between different populations, locations, and species, here They're specifying a different trend, a different abundance year trend in different populations, locations, and species. And that's really important because in the random intercept model, they are specifying that by only specifying the difference in mean abundances, they're also specifying implicitly that all of the trends are the same for all populations, locations, and species. Now make of that what you will. But these approaches are also ignoring a really important issue, a really important structure within the data that I mentioned earlier. If we look at Tobler's first law of geography, everything is related to everything else, but near things are more related than distant things. And the ethos of this is so implicitly evident within the data structure of these large biodiversity data sets. For instance, let's look at a given time series. We would imagine the abundance value in point 1 to be more similar to point 2 than we would point 8. So there's likely some temporal structure. We'd imagine that there is some spatial structure as patterns of environmental change are spatially clustered. If we look at the Amazon, they're not randomly picking spots of the Amazon to deforest. It's happening in this constant wave, this constant frontier. And then if we imagine the phylogenetic structure, species have this shared evolutionary past, and their intrinsic traits are dictated by this evolutionary past. And with species will have more similar traits when they're more closely related. And in turn, we would imagine that their responses to environmental change will also be more similar when they're closely related. So there are these 3 different axes there. There's the temporal, the spatial, and the phylogenetic axes that we are arguing are likely present in the underlying structures of biodiversity data. And if we sort of imagine what that would look like here, if we've got a bunch of abundance time series and we're looking across and we've got a phylogeny on the right hand side, we'd imagine that the abundance time series that are would be more similar in the species that are more closely related. And in essence, we end up with 2 almost distinct clades of values here. But why does this matter? Well, one of the core assumptions of our statistical approaches, the statistical approaches we use to describe this data, to extract signal, is that the data are independent. And if that assumption is violated, if the data are not independent, if they exhibit these spatial, temporal, and phylogenetic structures, it means one of the core assumptions of our models is violated. And so it begs the question, what do we want our model to look like? What would we aim for? Well, here's just an example of the random intercept and random slope model first. Like I said, the random intercept describes these mean abundances between different population, species, and locations, but everyone has the same trend. The random slope recognizes these different trends, but it doesn't account for this non-independent structure across the 3 axes of time, space, and phylogeny. What we really need is a model that can simultaneously account for these spatial, temporal, and phylogenetic structures. Those structures can be embedded within the model. And, to some degree, we already do this in the literature. Phylogenetic comparative methods are becoming increasingly common. Spatial structures are increasingly common, and temporal structures are increasingly common. But when we looked at this in a literature review, it was evident that they were, whilst being common, they were still being applied in less than 10% of cases. And even when they were being applied, they were being applied just as largely with just one being applied for at one time. So they might just account for phylogeny. And very rarely did they account for 2, but they never accounted for 2 simultaneously. They'd account for 1, and then they'd account for phylogeny, and then it'd account for time. But that's just not quite good enough, because then there's still a risk that there's some non-independence issues. So what we need is a model that can do all 3. And so as part of this postdoc at the University of Sheffield, where I've been working with Rob Freckleton, Andrew Beckerman, Dylan Childs, amongst others, we've been sort of redesigning what these models should sort of look like. And to do that, we take the random slope model as our base model. So it's got all the same terms as a random slope model. But now we're suggesting that there is some autoregressive correlation between a different time series. So there is some temporal structure. And then we also include a distance matrix and a phylogeny. And this specifies that our population trends should covary according to spatial structure and phylogenetic structure. In essence, we can include in a very general mixed model framework, so super flexible too, we can include the temporal, spatial, and phylogenetic structures. And then there's some really important potential implications of this. You know, if we imagine the scenario I introduced earlier, where we had these 6 population trends that generally fall into 2 different clades, if we move from the random slope to the correlated effect model, our expectation then would be that uncertainty will increase around the model, because actually these 6 independent trends in the random slope model are actually more like 2 separate clade level trends. And so our confidence is likely reduced. There is also a chance, though, that it won't only impact our uncertainty, it could also impact the mean trend itself. You know, for instance, imagine we have 100 different population trends for mammals that are generally pointing towards an increase. And then we have 2 population trends for amphibians that are generally pointing to a decrease. In an ideal, under the random slope model, when those trends are included, we would generally end up with this increasing and very confidently increasing trend. But in the correlated effect model, we're specifying that actually these 100 mammal values should only be equal to about the weight of the amphibian values. And so the uncertainty around the trend should increase. And so we decided to try and test these different model structures across 10 high-profile biodiversity data sets. Some of these I'm sure you'll recognize. You know, we've got top in the middle, we've got Living Planet, we've got bottom in the middle, we've got Biotime, we've got the North American Breeding Bird Survey on the bottom left. These are really high-profile data sets describing millions of abundances for tens of thousands of populations, locations, and species. And so we're comparing our 3 different model structures here. In the dark green, we've got the random intercept. In the lightish green, we've got the random slope. And in the gold, we've got the correlated effect model. And here, each of these different lines represents the collective trend, a term we're calling the collective trend. In essence, it's the average trend in abundance change across all species and locations. And there's some really important features in this. So firstly, it's evident as you move from the random intercept through to the correlated effect model that uncertainty increases. It doesn't just increase a bit, though, it explodes. For instance, the random intercept model underestimates uncertainty by about 40-fold relative to the correlated effect model. The random slope underestimates uncertainty about 3 or 4-fold relative to the correlated effect model. So we're talking really substantial underestimates of uncertainty. But as I mentioned earlier, we're not only expecting this uncertainty to be underestimated, we also expect to see changes in the mean trend. And for instance, if you look at the Living Planet data, which is panel C, we can see that under the random intercept model, we have a significant increase. On the random slope, we have a significant increase. And then under the correlated effect, we end up with a non-significant decrease. So we're seeing really substantial changes in inference of these high-profile data sets that have been super influential within policy, academic circles, and the public's understanding of biodiversity change. And so the question is, what is actually happening? What's altering our inference around these data sets? So here we've got on the y-axis, we've got the absolute difference in rate of change, so this collective trend coefficient between the correlated effect and random slope model. And then on the right-hand side, we've got the fold change in standard deviation of the correlated effect and random slope model. And then on the x, we've got the mean signal. And this mean signal here describes the amount of variance captured by the spatial and phylogenetic terms. So how much spatial and phylogenetic non-independence exists within the dataset. And from this, if we just focus on the right-hand side, it's clear that when there is a spatial and phylogenetic structure within the dataset, the random slope model tends to underestimate uncertainty. Okay, I've whipped through that really fast, but that was because I wanted to dwell a little bit more on this. So this has all been very inferential focused here, but the title of my talk was about prediction. And so before I actually talk about what this actually means for prediction, I just want to talk about what I call the prediction inference paradox. Within the whole field of ecology and actually beyond ecology into the whole sciences, we often try to think about whether we should design our model, whether we should choose our model based on what it can give us inferentially or what it can give us with regards to prediction. For instance, let's say in the world of SDMs, we often think about trying to build all of these different ensemble models to try and find the most effective and generalizable structure of how of biodiversity patterns. Oh, hello, Maggie. And Mrs. Um, but when you do that, there is a risk that your model, you throw in loads of parameters, thousands of parameters in order to improve these predictions, but at the same time, those parameters become almost unexplainable. You compromise inference. But I don't think that we should be developing models that either offer prediction or inference. I think we really need to be developing models that offer both. And this is already starting to happen, I think, in the world of AI. Historically, people would build these really complex deep neural networks with thousands of parameters, and they'd offer this whole new insight and prediction, really improved prediction. But at the same time, we had no ability to infer what these predictions, why we had these predictions. We couldn't extract the parameters effectively. But even now in the world of AI, they're starting to move away from these pure black box approaches, more into trying to actually explain and describe what these given parameters are doing. And so the reason I've just gone on that spiel is that I believe recognizing these dependencies, recognizing these spatial, phylogenetic, and temporal structures, not only improves our inference, not only makes our inference more robust, it also has the potential to improve prediction. Let me show you. So we've got the three different models on each of the different rows here. So random intercept, random slope, and then at the bottom, we've got the correlated effect. Then on the different columns, as we move from left to right, we've got an increasing ecological scale. So we've got population level on the left, site level in the middle, global level on the right. And let's just work through these. So in the random intercept model, it's really evident that it's a poor representation of the population level dynamics. It just doesn't fit at all. The random slope model does comparably better, but is still well off and completely misrepresents the dynamics that are evident once you recognize the temporal structure in the correlated effect model. By including that AR1 term, we're starting to capture this residual variability, this non-linearity from residual variability. And that's not only important when you're trying to actually predict the actual population abundances, but as we move towards the site level scale, you can also see that by recognizing this temporal autocorrelation, actually our uncertainty around the site level increases. So we get a more uncertain estimate of population of change in the site level trend. As we then move towards the global level trend here, we have each of the little gray lines represents a site, and the black line represents the average across sites, and the black shadowing is the uncertainty around the average. What we can see is that the random intercept model and the random slope model massively underestimate the uncertainty and the heterogeneity within these site level trends. Whereas in the correlated effect model, we're getting a far closer and more accurate representation of actually what's happening within the data. And then if we project these onto from an arbitrary baseline of 100, this far right-hand side is sort of like the figure I showed earlier for the 10 different data sets. If we project these trends from 100, it's really clear how our understanding of biodiversity change is completely different depending on what model you choose, and how there's a really big risk that if you just use the random slope model, you're going to massively underestimate uncertainty in the data. So by embedding, I just want to actually go back on this global level trend. The reason for this uncertainty isn't just the temporal structure now, it's also because of this spatial and phylogenetic covariance between the different sites and species. So that's what drives the uncertainty here. Um, and by more accurate, what's the word? By better representing these structures, these implicit data structures, we actually see substantially improved prediction and forecasting ability. So here we have the three different models, and we've asked each of these models to predict the final abundance value in half of the time series. So we've removed, for half the time series, we've removed the final abundance value, and we've then asked each of the models to predict this value, and we've tried to see which one comes out on top. Unsurprisingly, the correlated effect model offers substantially improved predictive ability, forecasting ability. And this is a 1 year forecasting ability, so going 1 year ahead. But we see an almost identical picture if we look at trends, where we can also estimate trends beyond the known data. For instance, if we take the priori structure of a phylogeny and the planetary structure we have of latitudes and longitudes, we can use that phylogenetic and spatial structure that we've effectively captured through covariances to actually predict across the phylogeny, to predict on species not within the data, and to predict on locations not within the data. And we can start to get a clearer vision of actually how biodiversity is changing beyond those simple lines of decline that we introduced at the beginning. So in summary, not of the whole talk, but of this section, inference, by recognizing these data structures, these spatial, phylogenetic, and temporal structures, we deliver more robust inference, and our prediction is more accurate. So we resolve this prediction inference paradox, partially at least. Before I move on from this, I actually want to just jump back to this slide because there's something important here. If we look at these 10 different data sets under the correlated effect model, at 95% credible intervals, we fail to detect a single increase or decrease in the mean trend. So we cannot find any evidence of a decline or recovery in the mean trend using the correlated effect model. In contrast, we do find increases and decreases in the other models. So that's suggesting that there is not this clear evidence of like contemporary biodiversity loss, which we can see, and we can definitely see in other data sources. For instance, we look at the red list index. There is clear evidence of biodiversity loss, but we just can't really see it in this data. And there's a whole load of reasons why I think that might be that I discussed at the beginning. For instance, we generally monitor populations most in protected areas, and we're not effectively recognizing that. The areas where biodiversity is most likely suffering, we are the areas that are hardest to monitor. We do not monitor at the most impactful, the areas where humans are impacting the planet most. And we're not the first study to show evidence that there is not biodiversity loss. And I want to be clear, I'm not saying biodiversity is not declined. We just can't find it in this data. And we're not the first study to suggest this. The second thing I want to just note about this figure is if we look at the recent research that's come out, describing these biodiversity changes, Haas's group had a paper on freshwater recovery early last year. Roel van Klink had a paper on terrestrial that showed terrestrial stability and freshwater declines in Europe, or maybe vice versa. In essence, what I'm trying to say is there's been an awful lot of heterogeneity in how in how the literature is describing biodiversity change. Once we recognize this in the correlated effect model, once we recognize the implicit data structure, that heterogeneity actually vanishes. All of these ups and downs that are increasing at 95% credible intervals or decreasing, they vanish under the one common theme of enormous uncertainty. We can't detect any increases or decreases because things are just so wildly uncertain. Okay. So let's look back at this. Well, I want to see what the next slide is before I go on. Okay, let's look back at this. We've got this immense data set, incredibly complex, that we need to extract signal out of. When we finish that piece of work, which we're hoping will be out very soon, Uh, we sort of figured we'd addressed one issue, but there were about 10 others that we could have addressed. And so in the next piece of work that I want to talk about, we're trying to fit in as many of these advances that have happened in statistics and ecology in the last 20 years. We're trying to squeeze as many of them into one unified framework for modeling biodiversity change as possible. And so if we take a look at this data set again, I've already mentioned that there's some spatial bias, there's definitely some phylogenetic bias, there's temporal bias, there's bias in the features of environmental change, where we generally monitor things in protected areas. And all that comes down into this one broad issue of the sample we're working with is just not even remotely representative of the planet. And that becomes really problematic when we're trying to actually infer and describe biodiversity change. So let's imagine we've got this figure again. We've got this decline in biodiversity. Looks an awful lot like the Living Planet Index or the European Breeding Bird Index. And there's these indices are derived. These indices are actually derived slightly differently to the approach I introduced earlier. So we used a mixed modeling approach in the last piece of work I was discussing. The alternative approach is something we call a decomposition approach. And let me just explain what that is. This is the approach used by most indicators. And these indicators are all focused on trying to describe the change in local population growth rates. And so how does that happen? Well, if you imagine we've got a population trend. Sorry, I just need to tell my dogs off. Away. Down. Sorry. We've got a series of population trends with different population abundance estimates. And we're expecting these to be a little bit noisy. So one of the approaches to resolve that is they fit a GAM between these different population estimates to come up with a smooth trend. They then take this smooth trend and they calculate the interannual growth rate between each pair of observations on the modeled observations. Then, away, Benji. Sorry. They average those interannual growth rates to come up with an average growth rate per species per year. And sorry, I'm very distracted. Let me try and remember what I'm saying. Okay, so they average this to come up with a interannual growth rate per year. But the problem with this is by doing this aggregation approach, they're ignoring a whole array of different facets. For instance, even in the GAM phase, they are ignoring things like measurement error and the error in detection. They're also ignoring things like, the actual process of biodiversity changing. They're ignoring the environmental features. They're ignoring things like population dynamics, density dependence. They're ignoring a whole array of different things that I'm going to list later at the end. And so we decided, okay, without trying to reinvent the wheel completely, let's try and work within their existing framework of these indicator approaches, which have already got traction in policy, are already understood by a lot of the literature. Let's not try and reinvent the wheel. Let's just try and add to it and make it a little bit better. Iterate on top of the immense progress that's already been made in this in the last bed. Let's iterate on the immense progress made in recent decades. And so we've got this data set again with millions of abundance values over recent, spanning 50 years, thousands of species, thousands of locations. And one of the really fun things we can actually do now, the data has reached this almost like critical capacity, is we can actually start to build individual models of abundance change per species. So let's imagine we've just got this simplified model here where we're trying to estimate abundance in species site, species J, and time point K. And we've got a couple of different features in here. We've got the environmental features, so how the environment is changing, as well as the static environmental features like habitat type. And these can be characterized in a whole array of different ways, but let's just say there's some environmental structure to the data. Then we're imagining there's some species-specific responses, which we described earlier. We're expecting this because of the phylogenetic structure within the data. as well as some response diversity. And then there's some underlying spatiotemporal structure. These features, so in essence, if I was to summarize this, we've got these environmental features and we're trying to knit these environmental features into this spatial, temporal, and phylogenetic structure that I've just described as what I consider important. And ultimately, when we do this, we end up with this really nice like tensor product where we've got the estimated abundance pattern for a given species across the spatial domain at each different temporal level. And when you do that, you can come up with these really nice projections of abundance for different species. So this is the pattern of common buzzard density across Europe in the last 50 or so years. And you can see there's some the density patterns change somewhat as you move through time. This figure is actually only depicting the spatiotemporal structure and not the local environmental features currently, but that's a work in progress. So we can get these model-derived outputs of abundance. And then one of the really fun things we can start to do with these model-derived outputs of abundance is we can plug them into the existing approach for aggregating indicators. And now here you've got two different lines on each for 16 different species. You've got the original approach for deriving the species level trend, the original aggregated approach for deriving the species level trend. And then we've got the new approach. And this new approach is taking those model-derived estimates, plugging them into the same aggregation approach, and see the core idea of this is we wanted to see how things would change. And we get a pretty consistent pattern here, where under the new approach using the model-derived abundances, our abundance patterns are significantly lower, substantially lower than under the original approach. And so the question is why? Well, the only reason we could end up with this pattern is if we're exhibiting something like without trying to go into the imputation language too much, we're exhibiting some like missing at random structure or not missing at random structure in the data. Where, if I was to word it simply, the data we are collecting are more prone to exhibit an increase than the data we are not collecting. So there is a bias in the data collection where you are likely to exhibit increases, where all of the data we have is likely to increases, whereas the model-derived data, where we're accounting for this by recognizing the spatial, temporal, phylogenetic, and environmental features, we're recognizing all of those, all of a sudden our estimates of abundance change are shifting. And if you've got questions about this, please do ask me, because I've just explained that terribly. And if we take this across those 16 different species, this is the general pattern of, again, the original indicators are more prone of showing an increase than the new ones. So using the model-derived information, we are more likely to see a decline than we are using the raw data. Now, I do just want to add a note here. At the beginning, I pointed out that all of these things were showing this like general decline. We don't actually see this here because we're working just with the highest quality data that actually tends to exhibit those biases even more strongly of like occurring in protected areas. So, but relatively speaking, we're still seeing this really stark difference between using the raw data and using an underlying foundational model of how biodiversity is changing. Okay, but is it worth it? Is it good? Is the new one we're presenting actually useful? Well, for the new model to be better, it has to reduce more error than it introduces. And what we're arguing is that the original approach, where they just take the aggregated index, is introducing error in the form of things like sampling bias, observation error, all of these different approaches. And so those errors have to, on this little seesaw, they have to be, in order to do better than that, we just have to make sure our current model is effectively capturing these spatial bias, effectively capturing these observational errors. At this point, I don't want to say whether this new model is better or not. We need to do some really, really rigorous testing. But you get the idea that this new approach of using the model-derived abundances is only going to be effective if it's actually better at capturing these underlying data structures than and eliminating these errors than the raw data. And so I think it's useful to think about what should that model actually look like? If we're trying to build like these foundational models of how biodiversity changes, which I think has so many different uses for what we'd want is we'd want a model that can sort of work at the like continental scale for things like, if we're creating new biodiversity frameworks like the coming Montreal one, we want models that can track our biodiversity change effectively across these massive global scales. But we know policy doesn't generally work at that level. It works nationally and regionally and even in some cases locally. Then you actually want the whole model structure to be flexible enough that it doesn't only give us continental outputs, it gives us outputs across this whole scale down to spatial scale, down to local taxonomic scale, from working across thousands of species in the spectrum of biodiversity down to even population level information. Wants to work across all of these different temporal scales. And that's a really demanding ask. But we've been trying to work on alongside some collaborators, we've been trying to work out how to do that. And so the first thing we need to resolve is this representative sampling issue. There's some excellent work going on by people like Robin Boyd and Ollie Pescott at UKCH trying to talk about this like non-probability sampling. We need to try and resolve this representative sampling. So we're trying to incorporate some of their thinking into these underlying models. Like I mentioned, the scale aspect is really important. We need it to be flexible enough that it can go all the way from continental scales down to single populations. We need it to be sensitive and accurately parameterized to environmental change. In this version I've just been talking about, we've included relatively crude, GAM structures on how species should respond to environmental change. But actually, I think for this to be generalizable beyond the known data, especially for species with no data or limited data, we probably need to try and embed some strong theory and theoretical expectations on how species should respond to different facets of the environment. And we're working on that now with things like the inclusion of thermal performance curves. We also need to recognize the observational error. When you're working on these data sets, there are so many zeros in the data, and it's generally unclear whether those zeros are actual zeros of extinctions or emigrations, or whether they're just simply misdetection. We also need to try and think about how this sort of works in a community and population dynamics perspective. The community one's a little bit harder because there's so many complex community processes going on. But even just the inclusion of things like there's a really cool paper by Kerry's group about a decade ago that showed in these time series about half of them exhibit density dependence and hit carrying capacity at some point in the time series. And if we're ignoring that, that's got pretty big implications for how you'd expect populations to change in, say, protected areas, where you wouldn't necessarily expect to see any recovery because it's probably already at carrying capacity. But all in all, what I think this means is that there's just an awful lot of modeling complexity that needs to be wrangled to try and actually build a model that can effectively describe the system. But this is a big system to try and describe, a big and complex system with noisy data. I spent the last few years trying to work on on resolving this and embedding these features into more complex models. And if my talk's accepted at EFI in Helsinki, I'll present actually about what this model actually looks like instead of just hypothetically describing it. There's some really fun opportunities to try and reimagine what we actually want these models to do and what they can do. Trying to embed the most cutting edge approaches. Today I've focused almost entirely on the aspects of biodiversity change, if any, on how we should statistically model biodiversity change. If anyone is interested in working on this with me, please do reach out. This is one of the underlying strands that Maria introduced at the beginning. Can we, because so my fellowship is focused on trying to understand the socioeconomic impacts on biodiversity. But the problem is it's really hard to disentangle those impacts when the underlying biodiversity models aren't quite good enough yet, in my opinion. So one of the strands is, can we try and embed these advances into the underlying models, and then we can start to develop better scenarios. Thank you.
Thank you very much, Tom. It was a really great talk. Fantastic. Thank you. Are there any questions? So far, just people clapping. Let's see. Yes, Istem.
Thank you for this great talk, Thomas. I was wondering, what were the reactions that you got to your study? Like, we basically didn't detect any declining trend in these high-profile data sets. Did you get any support, or did you met any resistance? What was the reactions?
I think for people that work with these data sets, it's actually not necessarily that surprising. Don Ellis had the huge paper out showing that there was winners and losers when you work with this data set, and that's to be expected. When we start thinking about actually what's probably happening, there is in the face of environmental change, one species is likely to decline, but something else will fill the niche. And then if we start thinking about these data sets representing not only the areas that are suffering environmental change, but also the areas that are exhibiting status quo, actually, when you average across all of these different features, it's probably unreasonable to expect to detect a decline across global scales. So actually, the people that work on this, I think, are less surprised. It's more the people that don't work on this that are more surprised.
Yes, Kara, go ahead.
Yeah, thank you for that. It was a really nice talk. I was curious about, so you said you did a bit of a review of some of these indices. And I was curious for those, if you saw, like, is there some sort of model selection going on, or are people mostly doing what they've seen like other studies doing or being done for the other indices? And then relatedly, like, how do you think, like, how challenging would it be to implement another modeling approach, and how to get that like taken up by people actually generating these indices?
Yeah, that's a really good question. I don't know the underlying philosophy that's dictated the research landscape, but my gut feeling is that it's actually been very difficult to implement new advances in the indicators, because once you've got some policy traction on it, you don't want to keep it's difficult to keep iterating and suggesting that you're going to improve it. Or look at like the Living Planet Index. It's had like one or two changes in its nearly 25-year lifespan. The last change was over a decade ago, despite how fast the field has moved and despite how many new advances have appeared. But I think that's just so difficult to constantly bring these new ones out, because you almost risk losing your credibility of your past one, if you see what I mean. And I think that we have to speak with some sensitivity around these issues, because they're also so easily misunderstood. What you're saying, I tried to make it very clear. I don't doubt that biodiversity is, you can't have the massive human impacts on our planet and not have suffered some biodiversity loss. So then when you're like, okay, we don't see any biodiversity loss, that doesn't, they're not the same thing, you know what I mean? So yeah, some sensitivity around it too.
Yes, we have, I'm gonna butcher your name maybe, Yussi. Am I pronouncing it correctly?
No, that's very good. Yeah, I really like the talk. I've been also thinking about that, like how people can go claim that there is no biodiversity loss when they they kind of infer only sites which are like very like in natural conditions. I also kind of did some similar work on that, like how communities change in Finland, and like how that change is associated with like environmental drivers, and found the same pattern, that, or kind of the same kind of bias there, that if you kind of look at over all sites, you find that, well, there is like not much kind of like environmental effects, but then when you kind of concentrate or make it like spatially explicit, you actually see that, well, actually the change is happening in many sites due to like because of like disturbance of the habitat. Did I even have a question here? But like I was thinking that, like, are you kind of planning to do some like a synthesis of that, like a spatially or temporally explicit synthesis of like how biodiversity is changing, and like or kind of saying something about like how much you can say of the like of like general biodiversity change based on these like well-preserved sites which are sampled?
Yeah, it's a good question. So not specifically about sites that are more protected, I'd say, but we are working towards the general vision at the end of this is to try and improve these approaches, improve these methods sufficiently that we can start to make these spatio-temporally species explicit estimates. And part of that would be effectively parameterizing how we'd expect a population of a given species in a given site to change if that site is undisturbed along this whole disturbance spectrum, if that site is not experiencing any climate change all the way through to a new, completely new climate spectrum. But it's trying to parameterize all of these features simultaneously without just running into massive complexity that you can't interpret it. So yeah, that is in the plan, but iteratively taking cautious steps, I'd say.
Yeah. Well, anyway, cool to hear your stuff in Helsinki in summer.
More questions? I think I have yes, Istem, go ahead and then I will ask my question.
Okay. Maybe mine are a bit tangential, but I'm not working in this area, but I was kind of wondering, what is the role of synthetic data experiments? Are you using some simulated data to build your models? Yeah, and that's one. And another question is, like, do you see any connection of your work to these digital twins of biodiversity that are being developed? Are there any connections or any collaborations that you have with those teams?
Yeah, so regarding the first one, we've used an awful lot of simulation approaches to ensure our methods are doing what we think they're doing. But we haven't necessarily used them at this point to their full capacity. You know, one of the interesting questions would be, if you can take, say, the correlated effect model, what sort of data do you need to actually detect any change? What does the planet need to look like in order to actually see a decline? What's data do you need to be collecting? And I think that's a really important question that we actually don't know the answer to yet. It was partially answered in some work earlier this year by, I can't remember who did it, someone in Enrique Pereira's lab. But that was prior to us producing a model that shows you need an awful lot more. So yeah, I think more is needed there. The second part of that is no, I've not got any collaborations currently there, but I'm definitely in like digital twins, but I'm definitely hopeful to establish them.
So I'll go ahead. Thanks, Istem. I'll go ahead with my question. So in terms of I think this is a repeating thing, that there's synthesis after synthesis, model after, always saying that we don't have enough data. We don't have enough data, or the data that we have is not appropriate for the purposes we're using them for sometimes. Or like you say, most of the high quality abundance data sets are from natural areas. I'm sitting in one of those, like the meerkat data, for instance, is one of the most high quality data sets, but it has been developed for completely different purposes. Had nothing to do with conservation, really. And so my first question is, do you think, or has the data improved through time, or are we still not collecting, better data for more species?
Yeah, okay. So I think the more ad hoc data collection schemes like that used by like the Living Planet, they are far more exposed to these biases than the more systematic data collection schemes like European bird or North American bird monitoring schemes. Arguably, I think we could trust the ones with the more robust data collection schemes far more than we could say the Living Planet data. That's not to say we can't trust it. We just have to use it, acknowledging that there's these differences in collection. My concern, though, if I just spin off that question a little bit, my concern is probably, I'm conscious we cannot, it's probably undetectable. We can probably never detect those past biodiversity changes effectively. We can probably never recover them now. So I think we probably need to start trying to reimagine and redesign how we should be collecting data going forward. If we want to be able to detect stuff, what spatial scale, what taxonomic scale, blah, 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 what do we need to actually do to collect that, to detect that?
Yeah, that's a very good point. Yeah, that's true. Yeah. Okay, thank you. Any other questions? Yes, Jody.
Yeah, thanks, Thomas. I was thinking about your figure where you were showing the differences between the three models. It was the green and yellow, and then thinking about the trends that you were showing. There were some different indices that had similar trends, and I think it was just my brain trying to lump things together. But I was wondering, I think it was like maybe the fisheries, large carnivores, and some of the insects that had the downward trends. And so do you think that's because of the taxa or because of the way that the data was collected that there's those similarities, or do you think that it was just by chance that they're showing those similar trends?
Yeah, no, I don't think it's by chance at all. One of the that's a really good point. So that figure later on where I showed, it was a matrix of 12 different plots going from the population scale through to the site, global, and projected abundances. One of the things that was clear is that once you start to refine the scale, once you refine the question, your inference starts to become more unified and at a far more precise level of estimation. And I think when you, for instance, the fish data set is generally describing fish abundances in the North Atlantic. It's a far more specific question than things like biotime, which are like, okay, let's try and understand everything. And so I think there's an interesting opportunity in there as well. This is sort of like the simulation question earlier, where you could start to refine the question down and see the point at which you can actually, say something with confidence. What taxonomic and spatial scales can you do that?
Yeah, that's great. And just really interesting. I mean, so much data and so, like you've been talking about, so many opportunities and additional questions to narrow in on.
Yeah, so yeah, I completely agree. Yeah, really interesting.